Hello everyone, welcome to this revision session on Chapter 9 Electricity of Grade 8 Physics. We all have come across electrostatic phenomenon once or twice in our life. So, like starting from combing our hair and uh, picking some pieces of paper from it, or getting a small shock whenever we touch any metallic object. So, there are two types of charges available in nature. One is positive charge, and the other one is called negative charge. So most objects are neutral in nature. They all contain equal number of positive and negative charges, but you can induce charges because of conduction. So we all have come across people getting shocked nowadays because of less humidity in nature, because it's summer. So we can see a person rubbing his foot on a mat. So the mat transfers all the electrons to the person's body, and the mat will get slightly positively charged, whereas the person will get slightly negatively charged. So when the person touches the doorknob, the charges will get transferred and there will be a small shock. Similar to that, we have one more example here. So in this uh, okay, in this example, so we have a balloon and we have rubbed it over a sweater, and the balloon gets negatively charged, and when I place the balloon somewhere away, it will get attracted towards the sweater. But when I take the same balloon and keep it near a wall, the electrons in the wall will get repelled, whereas the balloon is still getting attracted towards the sweater. So we can understand one property of this charge. The charges, if they are opposite in nature, they attract each other, whereas if they are similar in nature, they'll repel each other. So that's an important point. Like charges, like charges repel each other, like charges repel each other, and unlike charges unlike charges attract each other. Okay. Now, so here we are seeing a charge. So from this is a positive charge. So these are the electric lines of force. If I keep another positive charge, you can see how the electric lines of force behave, right? So they, since both the charges repel from each other, the electric lines of force will not intersect each other. Okay, they also repel. The electric line of force is the path taken by a test positive charge if you keep it near a charge. So if we keep a negative charge, you can see that the electric lines of force goes from positive charge to negative charge. So here this is an isolated charge. So always the electric lines of force will go from positive charge, and it will be always directed outwards. You can see in both the cases the arrow is outwards. But if I take a negative charge, the arrow will start from the positive charge, but the electric field line will go towards negative charge. Okay, so we'll place the negative charge back. So here the arrow is going from positive charge to negative charge. If you are asked to write an electric field diagram for two like charges, so we can take two positive charges or two negative charges, and we can draw how the electric lines of force would look like. So both, they all will go away from each other. So this line of force is actually the path traced by a small positive charge if it is placed near this charge. Let's say let's say this capital Q, which is my charge. If I keep a small charge, let's say small q, because this is positive as well as the charge is positive, this will take this trajectory and move away from the given charge. So if I have to write the electric lines of force between unlike charges, so I'll take one positive charge and one negative charge, and electric lines of force will always go from positive charge to negative charge. This is the electric field diagram for unlike charges. So there are many components which are used in our electric circuit. So the first one which you see is a wire. Right? This is the symbol used in the circuit diagram, and this is the picture of the wire, and it is used to carry current. So the next one is a junction. Junction is where the two electrical wires meet. Okay, that point is called as a junction. Then we have unconnected wires. So let's say if you write like this, right, it means that two wires are connected. But if the two wires are not connected, so you should not overlap them. Right? We'll just make it pass over it. This means these are unconnected wires. Then we have battery. If I just write one big line and another small line, this will be called a cell. This is a cell, whereas if I take series of cell, this will be called as a battery. So I'll just keep two lines. Okay. So the larger line denotes the positive side of the battery, and the small line denotes the negative side of the battery. Now there are other components like ammeter. Ammeter is used to measure current flowing through the circuit. Then we have voltmeter. Voltmeter is used to measure potential difference. You don't have to worry about galvanometer for time being. The next one is electrical bulb. So this is, we all know where electric bulb is used. It contains a wire, it will glow. Then we have resistance. A resistor will offer resistance to the flow of charges. Then we have open switch, and these are closed switch. Now here we have an electrical circuit. So we have a battery and we have an ammeter connected in series with the battery. Then we have connected this to a resistor and we have placed the wire back. But here it's an open circuit. That's why the charges are not moving. The circuit is not complete. Right? This is the positive side of the battery, this is the negative side of the battery. But once I connect this circuit, once I complete this loop, the electrons will start to flow from the negative side of the battery to the positive side of the battery. So there will be large concentration of electrons in the negative side compared to the positive side. But if someone asks you what is the direction of current, remember the direction of current will be from positive side of the battery to the negative side of the battery. So this is a convention which is followed in the scientific community. So this was devised back when Benjamin Franklin discovered charges. Like he named it as some charge as positive and other as negative, and we still follow the same convention even today. And the most important takeaway from this part is the ammeter should always be connected in series in the circuit, and the voltmeter should always be connected parallel to the component. Okay, if I want to find what is the potential difference between these two, between the resistor, so I should connect it parallel to the resistor. The next one is series connection. In series connection, we take two resistors, let's call this one as R1, the other one as R2, and we will connect these two resistors in series. So both of the resistance will add up, and the net resistance is given by R series will be equal to R1 plus R2. If we have 3 or more components, we can just add rest of the resistance. But in our case, it is only 2 resistors. But if you want to No, write this as a circuit diagram. We have resistor R1, then we have resistor R2. Now there's a ammeter connected here. Then we have battery. So this is the negative terminal of the battery, this is the positive terminal of the battery, and we'll complete this loop. Current flows from positive terminal of the battery to negative terminal of the battery. This is called as conventional flow of current. Then here this is R1, this is R2. But if I want to reduce this circuit containing only one resistor, I have to write what is the total resistance offered by both of these together. So the total resistance which are for resistors connected in series is R1 plus R2. So here the resistance due to this resistor is 10 ohm. The resistance due to the second resistor is also 10 ohm. The total resistance will be 20 ohms. So I can connect a 20 ohm resistor rather than two 10 ohm resistor and would still get the same outcome. So instead of connecting two 10 ohm resistors, I will now connect a single 20 ohm resistor. So this is the total resistance offered by both of these together. So such connections are called as series connection, and this is how you find the effective resistance due to resistors connected in series. If the resistors are connected in parallel, so they are connected end to end. So this is the positive side of the battery, this is the negative side of the battery. Now the electrons are going from negative side to positive side, but the current will be denoted to be flowing from positive side of the battery to the negative side of the battery. So here let's take the resistance of first resistor to be R1, the resistance of second resistor to be R2 ohms. So we have two resistors which are connected in parallel. If I want to rewrite this circuit, this is R1, this is R2. There's an ammeter connected. From here we have, it's connected to a cell. Let's say this is minus, this is plus, this is R1 and this is R2. So if two resistors are connected in parallel, the total resistance is given by 1 by Rp equals 1 by R1 plus 1 by R2. But if you have multiple resistors connected in parallel, let's say 1, 2, 3, 4 and so on, you have multiple resistors connected in parallel, then this pattern will continue. Then it will be 1 by R3 plus so on. Now if I want to calculate what is the total resistance offered by this circuit, I'll take 1 by Rp equals 1 by R1 plus 1 by R2, because we have only two resistors. So this will be equal to 1 by 10 plus 1 by 10. This can be written as 2 by 10. 1 by Rp will be equal to 2 by 10. Then Rp can be written as 10 by 2. So the value of Rp will be equal to 5 ohms. Even though I have connected 10 ohm resistance, I am only getting 5 ohms in total, right? So this circuit is equivalent to connecting only one 5 ohm resistor, so this circuit is equivalent to connecting only one 5 ohm resistor to the battery. So this will be 5 ohm. Alright, let's take the next question. Here our next topic of interest is Ohm's law. Ohm's law states that the current flowing through the circuit is directly proportional to voltage. Now if I want to remove the proportionality, I have to introduce a constant. So I will be equal to V divided by R, or I can say V is equal to I into R. where I is the current, the SI unit of current is amperes, SI unit of resistance is ohms, SI unit of potential is voltage. Here we can see that if I increase the voltage, then the current flowing through the circuit also increases. Current depends on voltage. Okay, voltage does not depend on current. Because there is a voltage, there is current in the circuit. Because you have connected a battery, there is current going in the circuit. Okay, so that's the concept. There will be many questions which are framed based on this. We'll try to look at a few of them later. The next concept is power. So power will be equal to voltage times current, and from our previous slide we know that V can be written as I into R. So if I know V equals IR, if I substitute this here, power can be written as IR times I, or power can be written as I square R. So this is the power through the circuit. Then if you want to find, let's say you have a heating coil and you are using a heating coil to heat up your water in your bathroom or something. So here the heating coil will have some resistance R. Now the amount of heat energy produced depends on what is the resistance of the coil, and the amount of heat energy produced is also proportional to what is the current which is flowing through the coil. If you make larger current flow through the coil, the heating effect will be larger, and this heat energy is also proportional to the amount of time the coil is switched on. If you leave the coil on for a larger time period, then the heat energy will be larger, heat energy dissipated will be larger. So we can write, or let's not, so here I'll say I'll reduce this to a 2 proportionality. So the heat energy dissipated is proportional to power. Heat energy dissipated is proportional to the time taken. So H can be written as P into I, and P is nothing but I square R. So H can be written as I square R, sorry, not P into I, P into T. So let's change this. This is P times T. So P equals IR, I square R. So H can be written as I square RT. You don't have to worry about the derivation. Like, derivations won't come for examination. Just have to know the result. Okay, knowing this is enough. Now we'll take a look at few problems. So we have to calculate the equivalent resistance for the circuit, which is connected to a 24 volt battery, and also find the current flowing through the circuit. Now here two resistors, R1 which is equal to 4 ohm and R2 which is equal to 6 ohm, are connected in series. Now if I want to write this as a single resistor circuit, I have to calculate what is the total resistance offered by both of them together. So here we can write total resistance, which is Rs, because these two are connected in series, to be equal to R1 plus R2. So this equals 4 ohm plus 10 ohm, 4 ohm plus 6 ohms. So which is equal to 10 ohms. Now we know that the resistance through the resistance offered is 10 ohms and the potential is 24 volt. If I want to calculate current, I can use Ohm's law. V equals IR. If I want to find current, I can be written as V divided by R. So V is 24 volts and resistance is 10 ohms. So current will be equal to 2.4 amperes. The SI unit of current is amperes. We'll take the next question. So in this question we have to calculate the current flowing through the given circuit. Here we have two resistors which are connected parallel to the battery. If I want to reduce this to a circuit containing only one resistor, I have to find what is the total resistance offered by both of these. R1 equals 4 ohm, R2 equals 6 ohm. For parallel resistance, the total resistance is given by 1 by Rp equals 1 by R1 plus 1 by R2. This will be equal to 1 by 4 plus 1 by 6. Next, we have to take the LCM between them. So this becomes 6 plus 4 divided by 24. 1 by Rp will be equal to 10 by 24. Rp will be equal to 24 by 10, which is 2.4 ohms. So we found out the resistance. Resistance is 2.4 ohms and voltage is 24 volt. If I want to calculate current, V is equal to IR. You should always start from here. I equals V by R. So 24 divided by 2.4, and this will be equal to 10 amperes. Current flowing through the circuit is 10 amperes. Remember, we are not calculating what is the current flowing through each and individual component. So 10 amperes are flowing through the circuit. So if I am measuring that current, I am measuring it somewhere here. So this is my ammeter. Here I am calculating it to have 10 amperes of current flowing through this part. But the current flowing through this part and this part will be different. So because the current is being split, here the resistance offered will be larger compared to this part. So more current will flow through 4 ohm resistor compared to 6 ohm resistor. Next, we'll try to write a question which contain series as well as parallel circuit. Let's say we have two resistors which are connected in parallel. Then I have a third resistor which is connected in series with it. But I also have a fourth resistor which is connected parallel to all these. Okay. So let's say this resistor has a resistance of 10 ohm. This resistor also has a resistor of 10 ohm. And let's say this is R1, R2. R3 has 15 ohms of resistance, and R4 has, let's say, 20 ohms of resistance, and all these are connected to 10 volt battery. This is 10 volt battery. So first let's try to calculate what is the total resistance offered by this part of the circuit. So R1 and R2 are connected parallel to each other. So because they are connected in parallel, I can use 1 by Rp equals 1 by R1 plus 1 by R2. So this will be 1 by 10 plus 1 by 10, which is 2 by 10. 1 by Rp is 2 by 10, then Rp will be equal to 10 by 2, which is 5 ohms. The resistance offered by both of them together, both R1 and R2, will be only 5 ohms. But this 5 ohm is connected to 15 ohm resistance, and these two are connected in series. Then the value of resistance should linearly add up. So the total resistance in this part of the circuit, right, because of R1, R2 and R3, will be equal to 5 ohms plus 15 ohm, which will be equal to 20 ohm. Because of R1 and R2 and R3, we have 20 ohms of resistance. So this is equivalent to writing a 20 ohm resistor connected to another 20 ohm resistor, right? That is R4, and these two are connected in parallel. So let's say we have a battery here. So this is 20 ohm, this is also 20 ohm, this is 10 volt battery. If these two are connected in parallel, we can find the total resistance. If I want to write it as a single resistor circuit, I can write this to have a resistance of 1 by Rp equals 1 by R1 plus 1 by R2. So this will be equal to 1 by 20 plus 1 by 20. 1 by Rp will be equal to 2 by 20. So Rp will be equal to 20 by 2, which is 10 ohm. So if I take all these resistors R1, R2 and R3 and R4 together, they only add up to 10 ohms of resistance. So instead of connecting all 4 of these together, I could have just connected one 10 ohm resistor and that would have done my job. So here I have connected this to a 10 volt battery. If I want to find current, I know V equals IR, I equals V by R. So this will be 10 divided by 10, which is 1 ampere. So this is the amount of current which is flowing through an ammeter which is kept here. Okay. So 1 ampere of current will be flowing through this ammeter. So that's it for this video. Thank you.